like in physics, we would say, we've said things all year, like if we have constant acceleration, in other words, velocity is changing uniformly, that if let's say we start off at rest and end up going 60 meters per second, what's our average velocity?
60 meters.
What is it?
60.
Well, we start at rest and end up going 60 meters per second. What's our average velocity? 30, right? Because we just add them up, divide by 2, right?
Oh, yeah.
Because whenever you call it uniform.
Because we called it uniform. Okay, so let's defend this a little bit. Let's make sure that this really works. So, a couple things. Now we're talking in calculus now about areas under curves. So it's time for us to go back and revisit kinematics for just a second. I want to show you. We've talked about this in physics, but not much earlier in the year. So if we take a velocity time graph, and let's represent the story we just told. We're going to start at 0, and we're going to end up at 60 meters per second after, I don't know, it doesn't even matter how much time. After 10 seconds. Okay. So, we'll go by twos. So there's 10 seconds, and there's 10, 20, 30, 40, 50, 60. And we're doing meters per second. Okay, so then here's our, okay, what I want to do here, okay, yeah, that's fine, okay, so it's a property of a velocity time graph that the area under the velocity curve is equal to total displacement, okay? So in other words, we could add up the area under this curve, and fortunately the curve is geometric, so we can just find the answer quickly, and we can know what the displacement of the car was, whatever it is we're dealing with, right? So what is it? 360 meters per second times 10 divided by 2, so 300 meters would be the units, right? Does that make sense?
Wait, 300?
Because it's going, the height of this is 60 meters per second,
Yeah.
right? And the width is 10 seconds. 60 meters per second times 10 seconds times 1/2, because it's half the base times the height for a triangle. Okay? So we're going to get a total area of 300 meters. So that's our displacement, right? Okay, well, we always said, though, we could just treat this as having an average velocity of 30. Okay? That's okay. So an average velocity of 30 implies, well, what would happen if we just assumed instead that the object was traveling with its constant average velocity for 10 seconds? What would that curve look like? It's like that, wouldn't it? And so the area under that curve would just be, well, half of 60 is 30 times 10 is 300. So it worked, right? What we've been doing all year has been correct, fortunately, right? That tells us something kind of interesting, though. We were able to resize or reconfigure this area into a more convenient shape, right? That's really all we did. We took a changing velocity and we reconfigured it into a rectangular constant velocity shape. And that defined for us this important number, 30, which we called the average value of the function, or the mean value of the function. We just use that, right? Okay, that works great. But what if? What if we take the same situation and it's not so well behaved? What if we've got something like this, let's say? Let's say that our velocity is now changing non-uniformly. Let's say our velocity is changing with it's as speed squared. So we're kind of, our rate of acceleration is increasing, right? So it's going to look something like this. We're going to start at 0, and we're going to do something like that. I didn't mean to go negative speed there. I meant to go like that, how about? Okay, so let's say that the velocity function here is just, I don't know, let's just say it's 10t squared, and we're gonna do this for 2 seconds, how about? Okay, so now, okay, so what's the height of the curve at 2? It's supposed to be 10t squared, sorry.
Plug in two.
Two squared is four.
40.
And
Okay. So this is at 40. Do you think our average this time is 20?
no.
Probably not. Probably not.
Why?
This is a different situation, isn't it? Because now, if I started off with the area under the triangle, and I didn't draw this very well, but if I had cut it right here, and then just kind of hinged that piece around and flopped it in there, it would have fit perfectly, right?
Mhm.
And the height would have been 30. That's not going to happen here, though, is it?
No.
There's not nearly as much area under the curve this time for the height. It's a skinnier curve. And so, and I can't even cut it and flop it over anyway. It doesn't work, right? I'm going to have to do something different. I'm going to have to bring out my two-dimensional calculus grinder, and I'm going to have to grind this function down so this, this blue area, and I'll see if I can be really tricky here. This is a challenge because I'm really not very tricky. Let's see if I can. Really? I think I might have to just do the whole thing.
Why are you doing that?
There, how about that? Okay. So if I bring in my calculus grinder and I grind this thing down from above, and so I'm gonna, as I bring this thing down, I'm gonna grind this up into calculus rubble, and it's gonna fall down the slope. By the way, it's gonna be trapped between these. Infinite walls at 0 and 2. So the rubble falls back this way. It can't fall to the right. It falls to the left. And it packs in perfectly, right? So it's same density as it was here. As I grind this thing, when I get down to back here, I'm going to fill in a little rubble there. And eventually I'm going to get to a point where I can stop grinding because the rubble has filled in all of the gap, and so it's level, right? See what I'm saying? That would define for me, if I could do that, that would define an average value for the function, wouldn't it? In this case, an average velocity. You see what I'm getting at? So we don't know where that's going to be, but let's just assume that it's like, I don't know, like right about there maybe. Let's just assume that that's where I'm going to be when this rubble fills in that gap right there. Okay? That would define for us what we might call V bar, okay, average velocity. How can I do that?
Finding the derivative.
Well, it's related to it, yeah.
Find the antiderivative.
Yes, it is. You're right. This is definitely integration, maybe. So let me remind you about one thing. What's true here is that the area under the triangle equals the area under the blue rectangle. What's got to be true here then is the area under the blue curve has to be equal to the area under the orange rectangle. Okay? How are we going to do that? I guess in order to do this, I would probably have to know what the total area was, huh?
Yeah.
Right? Do it.
Yeah.
If I knew what the area was, this wouldn't be a big deal though, would it?
Not a big deal at all.
Because calculating the area of the orange rectangle is just length times height, right?
Yeah.
No big deal. And we know the length is 2. Right?
Find the antiderivative.
Okay, so we're going to have to add up an area under a curve, which is calculus stuff, right? That's a definite interval. represent that? This blue area is equal to what?
2 times the F.
Summation.
Okay, so the integral of,
0 and 2, whatever.
well, of
10t squared.
10t squared, because that's defining the curve, right?
And you have to have the dt after.
Yep. dt at the end.
Equals.
Okay, I'm not done.
Blocks of a 2 and a 4.
So I'm
0
going,
and 2?
I'm going from 0 to 2. Good.
Oh, 2,
Right.
why?
Because that's 2
Just
and
that
that's
value.
0, right? So those are my values of A and B. So everybody got this now, right? So this is defining for us the area under this curve from this t value to that t value. Normally b out to it. For us, t this time, right? Well, that's not a hard integral. We can do that.
We can do this.
What's the, I can take the 10 out front, right? I don't even maybe need to. What's the antiderivative of t squared?
10 over 3 t cubed. T
Yeah,
cubed over
okay, so we're gonna get t cubed over 3 and then times 10. So we're just gonna get 10 t cubed over 3, and let's just write it like this. Remember we had this big discussion yesterday about how we can pull things out front when we're evaluating a function. It's not that big a deal, but well, maybe it's the day before. I lose track of my days. So I could either include the 10/3 in here, or why not just leave it out front? So what is the quantity 10 to the third power, 10 cubed, evaluated from 0 to 2?
0
1.
for 1. And then
Well, okay, but I'm gonna always start with the top limit.
8.
So I'm gonna get 8 minus 0, right? So the answer is just gonna be 10/3 times 8, which is 80/3. That's the area under the curve, for sure.
Easy.
Okay, so if that's the area under the curve, then I know that that's got to be the area of the orange rectangle, right?
And then you guys do that. And then you guys do
Y 2. 2 watch it.
Oh,
No.
Darn it.
You should have put it in the right.
oh! That's not what it was supposed to be.
That's pretty cool though. That's pretty cool.
It is pretty cool, but it's just not what it was supposed to do.
How'd you do that?
I don't know. I don't think I could probably repeat it if I tried.
Do it again. I love this how you say it.
Yeah, that's a computer. That's not weird.
It sounds like when you play a game and you like die off the fish and then the sound goes.
One more time. Let's try this.
I'm so excited.
Oops.
Oh. Is that what it's
Oh!
Oh, sort of.
Hey, what's the
Is that what you wanted it? And now go to the circle in the orange.
I want to fill in a little bit.
Fill in the little white.
Yeah, try putting on the white
Oh.
side. No.
Do it, do it. Oh!
Oh.
Oh,
Hey! So,
Oh, you got that 0 down there.
yeah, I don't know how I got that. Okay, anyway, so if we know the total area of this orange shape is 80/3, and we know that the width is 2, what's the height?
40/3.
Yeah, right?
What? How did you
Yeah.
divide
Well,
it by
because
two?
whatever the height is, call it h. 2 times h has to equal 80/3, right?
Well, 2 black.
You betcha, right?
So you divide by 2.
So divide by 2. So it's 40/3. So if the height is 40/3, then that's the average velocity. How about that? Right?
That's awesome.
So,
What is 40/3 in real numbers?
I don't know, what is that?
Wait, why did we need to know that?
13.3 repeating.
Why did we need to know 43rd though?
Because maybe we wanted to know what the average speed of the car was.
Yeah, think that.
And a meaningful average speed, because think about it, an average speed should be the speed where you could say, okay, I can either drive for 2 seconds with this bizarre velocity curve, or I could just put the cruise control on what speed and travel for 2
43rd.
seconds and go the same distance. That's what an average speed really should mean, right?
Okay.
Okay? Okay.
That picture's
Boo.
Okay, so if I wanted to define an average value of a function on an interval, right? Then all I've got to do is the same thing. I've just got to divide the area under the curve by the width of the interval, right? Because that means all I'm going to do is I'm going to trade this bizarre area for this rectangular area, right? And we'll call this, I think they call this in the book f of c, where c is the place where you have your average value. It's kind of a weird way to do it, but what it stands for is the average value of the function. Okay. You can call it anything you want. That's what they call it. But if I want to know what this is, all I've got to do is figure out what the area is and divide by the width of the interval, which is b minus a, right?
Yeah.
Okay. The area under the curve is just what we get from taking the definite integral rule, right?
Yeah.
Okay, so then we really come up with this relationship. The area under the curve, f of x, from a to b must equal the width of the interval times the height of the interval, right? So then we could define the average value of the function as area under the curve, its definite integral, divided by the width of the interval.
Well,
That's
that
it.
is complicated. I would not.
Well, it looks complicated, but it's really a pretty simple concept, right? Area under the curve divided by the width of the interval tells you the average value of the function.
You just did that.
Yeah.
Wouldn't that be C equals, not F of C?
Well, okay, so then what does C represent? So then C represents the places where, so C would have represented this.
I thought F of C was the height.
Well, C actually, in the language of the book, and this is pretty standard, C would represent this value right there. So C is going to be the one value of t, for example, where our car was actually going its average speed, which was 80 thirds.
Ah.
Okay. Now that could happen more than once, right? I mean, it could pass through that if the curve goes up and down. You know, maybe it passes through its average value more than once, and then C could have multiple values. So in this case, here, C would be, so this would be the value of C right there, right?
C is what again?
So C is the value of the independent variable, typically x, where the function has its average value on an interval.
I thought V bar was,
It is. So we called this V bar.
yeah.
So what we're going to say now is that if C is when the function has the height of its average, then whatever the value of the function is at C, so that point right there on our curve, whatever the y value is, that defines the average value of the function.
Okay.
Okay? But honestly, many times, that's a pretty backwards way to go around it,
Yeah.
because we typically don't really care
Yeah.
what the value of x is. We usually just want to know what's the value of the function, in which case it'd be easier just to call it something like f bar. Okay? That's just in the book, that's what they call it. Okay? Does that make sense?
Yeah.
Okay. All right. I think I'll just do a little chunk every day and then let you work. How's that sound? Or would you rather finish up today?
No.
Let's just finish up today.
Can we have a work day tomorrow if we finish up?
Yeah.
Oh.
Yeah.
Yeah.
Okay, last thing, and this is pretty easy one. So by the way, that's called the mean value theorem for integrals. It's in your book. So the last issue is what we call the second fundamental theorem of calculus. And what this is, oh man. Do
Can I go to the bathroom so quick?
You bet.
So quick.
So quick.
Better be so quick. Yeah, you're not like 15. Maybe you're not. Maybe a minute. Okay, just add 20. You have that 1 minute. Can she practice off? Especially if it's Kiri wearing birthday hats.
really, if I'm honestly, if it's summer dry, I'm just gonna ask if I can sit there. Yeah. Bad babe.
Okay, so this is a great trick. This is one that always like pops up on the AP test a few times, and it's so easy. This you can eliminate a ton of work by using this trick. On the for example, it shows up all the time on the AP calculus.
Could we have taken that test if we wanted?
Yeah,
Might not have been.
yeah. I don't think we're quite far enough to be right where we want to be though. So what does this mean? Okay, you gotta really focus in on this for a second. So this is saying if we've got this function f, right, and the area under the function f is determined by this part in the orange box. Okay, t is what we call a dummy variable. T is just in there to sort of carve out the shape of the function. X is going to be a specific value of t in this case. So what does this really mean? So if I've got some function, let's draw a picture to represent this. If this is the t-axis, and let's say this is f, what if we want to go from a up to some value x? Okay. And the area under that curve then, x is a variable. So would you agree that the area under that curve is going to be a function of x? Because if x is out here, the area is bigger. If it's back here, it's smaller, right? So then we could call this in here, we could call this some function of x. Let's just call it, how about a of x for area?
Dude, it's that first f of x you got open like. Right after the summation.
No. It's not.
Wait, why is it called area of X? The area is?
Say it again.
The area of the thing is there?
Yeah, it is. Right, the area
Now you screwed it up.
the area under the curve. So the area under the curve is going to be a function of x because x defines where we stop adding up the area, right? Okay. Now, look what we're doing up here, though. We're not actually calculating the area under the curve. We're calculating the rate of change of the area under the curve. Right? See what I'm saying? Okay, so that's different, right?
That's like the height.
Well, it's kind of, it's like the slope of the area versus, area versus x. Okay, now that's going to be different though. I want you to, if I sweep out area to the right at a uniform rate, right, so I'm just going to, let's say that my hand represents the right-hand edge of this interval. As I sweep that along, wouldn't you agree that I'm going to be sweeping out area faster here than I was here?
Yeah.
How come?
There's more.
Because the curve's taller, right? The value of the function is greater. Agreed?
Agreed.
But the change in x is the same the whole time. Just call it dx, right? Height is bigger here though. So doesn't it just make sense that the rate at which we're sweeping out curve has to depend on the height of the curve only? F of x. See what I'm saying? The value of this function evaluated at the endpoint has to be proportional to the rate at which we're sweeping out area. Where the curve is bigger, the rate of change of area is going to be bigger. And it's going to be an exact correspondence. See what I'm saying? So all you got to do here, though, is you've just got to, when you're doing a problem like this, you have to just recognize this little trick. That if you have a variable at the upper limit, and that is matched by the variable of differentiation, then all you do is just whatever the dummy function is that's determining the shape of the curve, the value of that function at x is the answer, right? Let's do an example.
Yeah, that makes
So, yeah, it'll help a bunch, I guarantee it. So what if we had something like this? The derivative with respect to x of, let's say, the integral of t squared minus the hyperbolic cosine of
This is not a good example.
2t. Okay, I'm well aware of the fact that you guys don't not important, you don't need to.
He's just showing how pointless.
Yes.
From negative 911 pi up to x
It's zero.
is equal to,
X.
not x,
Recipe.
it equals x squared minus the hyperbolic cosine of 2x.
What? Well, that's all.
Wait, is that a delta T or an S?
This is right here,
Yeah.
that's a D. That's supposed to be, it's a real crappy D. It's supposed to be- Okay, you see the pattern?
Yes.
The pattern is just that whatever this function is here, right?
Only if there's T's in there? What if there was a Y?
Wouldn't matter. If this is a y, it doesn't make any difference. If this is a different variable than this one is, it really makes no
What if
difference.
it's the same? It's X,
Okay,
X squared
technically-
minus cosine.
So you could even make them the same, it's just confusing to think about. But
Okay.
it would work even if these were x's and that was an x, it'd be fine.
Why'd you choose 9/11 and not the
I don't know,
9/11?
it's subconscious,
Talk
not
about my
sure.
birthday.
Conscious.
Yeah.
Oh,
Guilty.
Yeah, oops. Okay. So that's the answer, right?
Yes.
All you have to do in this case, if the bottom is a constant and the top is a variable, is plug that in, okay? But what could we do, how about if I did something a little different than that? What if I said instead, the derivative with respect to x of the integral, we'll just make it easy, how about like x or t squared plus 1 dt from negative x to positive x. Okay?
It's still gonna be X squared plus 1.
So wouldn't this be the same thing?
Yeah, 0. No, it's not.
Well, no, it's actually, you know what? It's not gonna be 0. But,
They're not really the same.
well, okay, I could have made it different than negative x too. We'll make that jump in a second. But we have some properties of integrals, right? We could arbitrarily pick some value between x and negative x. How about 0, right? That's got to be between the two, correct? So we could break this part right here up into, instead, we could do the integral of f of t. Yeah, exactly. dt from negative x to 0. Why is it keep moving? This virtual ink problem. Plus the integral from 0 to x of t squared plus 1 dt, right? Everybody agree?
Yeah, but then what?
Okay. And this one right here, we could instead just add the area up backwards if we want to, and make it negative. Remember that rule? We add up area from left to right as positive and right to left as negative.
Yeah.
So we could write it as minus the integral from 0 to negative x of t squared plus 1 dt, right? Plus the integral from 0 to positive x of t squared plus 1 dt.
You can switch one, not switch the other.
Sure. Yeah, all I did is switch that one. That's fine. Because they're being added, they're separate areas. Okay?
So how is that helping us get?
Okay, so then we're trying to take the derivative of this whole thing, right?
Yeah.
Well, so the same trick applies. So if I'm taking the derivative with respect to x of the whole thing, well, look what I got here. I've got a negative x, right? And a negative x. So I ought to be able to just plug that in for t, right? Here I've got a positive x and a, whoops, and a positive x somewhere. That's an x. Well, anyway, you get the idea, right? I can just plug this in for t, or I could plug this in for t, right? And so my answer ends up being,
2. No.
I'm going to get negative x squared plus 1 plus positive x squared plus 1. which is equal to 2x squared plus 2. Okay?
Okay.
Right? Make sense? Oh, but I had a negative out front, didn't I? Whoops. Forgot my negative out front.
It's not
Wait.
zero then.
How is it 2x squared when it's a negative x plus an x?
How is
Oh,
that
so
not-
that negative cancels out. Now I'm confused.
How is that not zero?
Okay, so it is going to be 0.
Okay.
Yeah.
So.
Right? So I'm going to get negative, because I got to distribute the negative. There's my negative, right? When I flipped the limits of integration, I had to put that negative out front. I'm going to get negative x squared minus 1 plus x squared plus 1. So I get 0.
No, I'm still confused. How is that not just 2x squared?
Because I've got
The negative only applies to that one, not to both of them.
So I was right, Mr.
Yeah.
You were. You were right. Okay? Make sense?
No. Why did it become positive all of a sudden if you didn't distribute the negative?
Well, because look what I did. I took these limits and I flipped it. And so that means I have to multiply by negative 1. Because now I'm adding up the area in the opposite
Then
direction.
why is it still negative if you distributed the negative?
Well, but what's negative 1 squared is what?
Okay.
Right? Okay. Okay, so moral of that story. If we see something like this, if we see an integral of f of t dt, the derivative of that with respect to x from, let's say, negative x to x, then what's that going to equal? Well, that's just going to equal f of x minus f of negative x.
So if it was negative 4 and 4, would it still be 0 too?
Well, for that particular function, it would. Yeah. Okay? Right? We could be even more general about this. What if we had something like, okay, this one's hard to show with the drawing. I'm going to give you the trick, but I want to see if I can get you to understand why the trick works in this one. This is, by the way, what I'm going to show you now is just kind of my own thing. This isn't in textbook. This is what I call my ultra generalized second fundamental.
Third fundamental theorem of caption.
No, this is pretty cool. This will take this to college because this always works and it's super cool.
Did you come up with it?
Did you put it in your own math book?
I haven't done that, but if I do write my own math book, I will do it. This is really cool though. In fact, I'm going to print it out for you so you have